So we're going to be working with two different differential equations that looks really similar, but with very different outcomes. So let's begin with y double prime plus 4y is equal to 0. And this differential equation will differ from the differential equation that we have on the right, y double prime minus 4y equals 0. Now, these two second order linear homogeneous differential equations will have two different cases. The initial one would have discriminant as greater than 0, and the other one would have less than 0, meaning that one would have the general solution with the formula of y equals c1, that's the constant, times e to the power of r1x plus c2 times e to the power of r2x. And the general solution, so this is essentially the general solution for the first case. Now, the general solution for the second equation is going to be y is equal to e to the power of ax b1 times cosine bx. Now, this b is as in beta, but I will be writing it using the English alphabet plus c2 times sine of bx. Now, we have these two general solutions that differ, and we will set this aside for now. And after we are in the process of solving this differential equation, then we will use these general solutions to see where they belong. Now, beginning with this first differential equation, they look quite similar, but yield different results. Y double prime plus 4y equals 0. Now, we first convert this into our characteristic equation, which is r squared plus 4 equals 0. Now, using algebra, we know r squared is equal to negative 4, and if we're trying to find r itself, we would have plus minus 2. And that is because if we square root both sides, we would get 2i. So our r is imaginary. It could be positive 2i and negative 2i. Now these roots right here are in the form of a plus minus di. A is alpha, b is in beta. And the real part, a is equal to 0, and the imaginary coefficient is b is equal to 2. So we know that a is 0, b is equal to 2. Now, with this in mind, we can look at our equations. For our general solution, we see that this one right here would be the right one. Now, we plug this right here. Now, the general solution for this differential equation would be y equals e to the power of 0x, which is just 1, parentheses, constant 1, c1, times cosine dx, which is 2x, plus c2 times sine 2x. Now we're going to go ahead and clean this up a little bit. Now, as a result, we would have y equals c1 times cosine 2x plus c2 times sine 2x. And this is the general solution for this differential equation. So we use this particular case where, since the discriminant b squared minus 4ac was less than 0, we can also verify that by quickly doing b squared minus 4ac. Now here, if we convert the characteristic equation to these ABC components, we know that this would be A, B, and C. And since we don't have a valid B, we know that this would be A as in 1 squared minus 4. A is 1, C is 1. Now the discriminant was B squared minus 4AC. So just to clarify that, B squared is 0. 0 squared minus 4A is 1, C is 4. So we would have negative 16 is less than 0. Now moving on to the second differential equation. Now they look very similar, but this one is with negative. Y double prime is equal to 4y. But before we do so, we're going to convert this into the characteristic equation. R squared minus 4 is equal to 0. R squared is equal to 4. Now r would be equal to plus or minus 2. Now this itself means that it is r, the root itself is negative 2 and the root is positive 2. This aligns with our other case, which is y equals to c1 times e to the power of r1x plus second constant with the same thing but for the second r. Now this would be our general solution, where we would do y equals constant 1 times e to the power of negative 2 plus constant 2 times e to the power of 2x. So the general solution for this differential equation is y equals c1 times e to the power of 2x plus c2 times e to the power of negative 2x. If you guys want, you could also rewrite this as y equals c1 times 1 over e to the power of 2x. And we can also take out the 1, but that was just for better visualization, plus c2 times e to the power of 2x. So the key takeaway is if we're going to be using this general solution, we have to remind ourselves that if we have two valid roots, roots R1 or R2, that are real numbers and are two distinct values, then we would use this general solution. If we have imaginary roots, then we would this equation